Hello everyone and welcome to the channel. In this video we'll add a 6551 UART to the computer and we'll be able to connect to it via USB from our laptop, and that's going to be the first time the computer can interact with us. So we'll be able to send it characters and have it reply to us, making it much closer to a real useful computer. So that's pretty exciting. I hope you enjoy. So until now, the computer didn't have any capability for interactivity. We have the LCD screen that I've been using for debugging purposes that serves as an output, but there is no input into the computer. And in the distant future, I want to have a computer that you can plug in on a monitor and use with a keyboard. But building a video display processor circuit or a PS2 circuit are things that are a bit complicated and that I want to do later, maybe not in this first revision of the computer. So I want to use a serial connection to talk to the computer from my laptop. And this is the same idea that what you would use to talk to the earliest computers that didn't have a screen or a keyboard interface. You would connect to them through a terminal and interact that way. So I want to replicate this for the first revision of this project. And so I will add a serial connection. The chip I'm going to use for that is the 65C51 from Western Design Center. It's designed to work with our processor, and it's a single channel UART with a pretty bare bones set of features, but I think it's good to get us started. One thing you have to note if you try to use this device is that there are some known bugs in the hardware that we'll have to work around in our circuit in order to be able to make efficient use of the device. I wouldn't necessarily recommend that you start with this device if you're building your own computer and want a UART. There are much better options out there that are more modern, more featureful, and most importantly, that don't have hardware bugs. I felt it was still an interesting device to talk about for didactic purposes, as it's quite simple and it's been designed by the same company that designs the CPU, and so it's great to work together. If you're starting a new project, I would recommend you maybe look at something like the 16C550, which is a much better modern UART that you can replace this with. Okay, so with this disclaimer out of the way, let's see what this device is all about. The 65C51 Asynchronous Communications Interface Adapter, ACIA. It's an easily implemented program control interface between your 8-bit microprocessor and serial communication. It has an internal baud rate generator, and we'll have to feed it with a 1.8432 MHz crystal for the device to work properly. And if we look at the interface diagram, you can see on the left here the CPU side, and on the right the serial communication side. So on the CPU side, it's a pretty simple interface. There's the data bus, RIQ, read-write, two chip selects. One is active high, one is active low. Then there are two register selects, so we have 4 registers internally. Then it needs a clock, the reset signal, and power. On the output side, it has a transmit data pin, a receive data pin, then inputs and outputs to the baud rate generator. We'll talk about them later. And then inputs and outputs for flow control and device detection. These are part of the RS-232 communication standard, which we're not going to be implementing with the circuit. I will only be using the transmit and receive, and I will implement software flow control because the UART interface I'm going to use and talk about later in this video only has transmit and receive. Going more in depth on the input signals, it's the CPU signals, there's nothing much to talk about. The RIQ pin is an open drain output, which means that we can connect several devices to the same RIQ input, and we'll have to pay attention to that because our 65C22, which is currently the only pin connected to the RIQ signal, is not an open drain output. So we'll have to add a diode or a logic gate in order to make this connection. Then here, depending on which register select is low or high, there is a number of operations that you can do when you're writing here on the left and reading here on the right. So reading, you will read all the registers of the device. And then for writing, you can write all the registers except the status register. If you do that, the device is programmatically reset. On the modem interface, as I said, we'll only be using the transmit and receive. And on the crystal, we'll have to supply a 1.8432 megahertz clock signal for the baud rate generator. So these are the baud rates that are supported by the device. Depending on the control register bits 0 to 3, we can go from a baud rate of 50 to 115K. And we can see here that we have two options to supply the clock. We can either use a crystal, and then we have to connect it between the XTLI and XTLO pins of the device, or we can supply our own clock, and then we have to connect it to XTLI and ignore the XTLO pin. I think I have enough information now to start building the schematic. So let's go into KiCad. All right, so this is our schematic of our computer where we left off the last time. I'm going to add a new hierarchical sheet to hold the serial communications. We're going to need the same set of inputs as the VIA. So I'm just going to copy them here. We just have to make sure that we use the second IO chip select. And then we can add our 65C51. It needs power and ground. These are all the CPU side pins connected. On the chip select side, I'm using the valid address pin to only select the chip when the CPU is outputting a valid address. And then I'm using the ACIA chip select, which is our second chip select in our address decoding, so that the chip has its own address range. And then I'm selecting the 4 registers using A0 and A1. And so yeah, this is everything on the CPU side. Then we need our clock. So for that, I'm going to use a CAN oscillator, which also needs power and ground. And this needs to go to pin 6. And the enable pin is a no connect. And that's 1.8432 megahertz. Then the second XTAL pin is a no connect. The receive clock we're not going to use, so that's also a no connect. Then we have our TX and RX, and then these we're not going to use at the moment, so the outputs are no connects, and the inputs I'm going to connect to ground. We're also going to need decoupling capacitors, 3 of them. One for the ACIA, one for the CAN oscillator, and one for the UART to USB adapter. So let's talk about the UART to USB adapter. So this device is going to output a transmit and receive data signals, and we need to interface to them with our computer so that we can talk to the device. And so for that, we need to use an adapter. And there are many adapters that you could use, but given that I want to do a through-hole only computer, the only through-hole USB to UART adapter that I was able to find is the MCP2221A from Microchip. And this is going to be a USB 2.0 to I2C/UART protocol converter with GPIO pins. So from our laptop, we'll be able to talk to our ACIA directly through this chip via the UART protocol. I'm not going to make use of the I2C capabilities of this chip. I'm only interested in the UART protocol converter. So let's go through this data sheet and see what this device is all about. It's a full-speed USB device that enumerates as a composite USB device. So it's a CDC, which is communication device class. So that's going to be the USB to UART. And this is going to be plug and play on the computer side. And the second device is an HID device. And so you're able to send HID commands to the device in order to change communication settings or talk to the I2C interface. So what I'm interested in, of course, is the UART options. So as I said, it's going to be plug and play. There's no specific driver that we have to write. It supports the same baud rates that the ACIA supports. And as I said earlier, there's only a transmit and a receive pin, so you can't do hardware flow control with this device. And then there's a number of other functionalities. So there are GPIO pins, which can be set up as activity LED outputs, so for transmit and receive. There's also a suspend output pin and a configured output pin. Suspend is going to be active when the laptop goes to sleep. So that's when you have to stop using current on the USB bus. So we're not going to use this pin because we're not going to be powering the computer from the USB bus, but it's there if you need it. And then USB config is going to be active when the device enumeration is completed. That means that the laptop is connected and it has detected the communication port. And so we'll make use of this one in order to detect when we can send data to the computer. So if we look at the pinout, it's a pretty small device. We're going to have our USB control lines at the top here, D+, D-, and then VUSB. SCL and SDA are going to be the I2C outputs, which we're not going to use. Then we have a reset, and I'm not going to connect this to the reset of the computer because I don't want my terminal to disconnect from the computer when I hit reset. I'll have to experiment with that. I'm not sure if that's the right thing to do, but we'll see. Then we have the receive and transmit pins, which will connect directly to the ACIA. And we have GPIO 0 to 3. And that's going to have some varying features depending on the configuration. So if we look at the configuration here, GP0 by default is going to be the UART receive activity LED output, which we're going to use. GP1 by default is going to be the UART transmit LED activity output, which we're also going to use. On GP2, we're going to have by default the USB device configured status, which we're going to use to know when we can send data to the computer. And finally, GP3 is going to be by default the USB/I2C traffic indicator. And I will add an LED on this, even though we're not using I2C at the moment, just for future proofing. So yeah, so as you can see, we don't have to change any of the GPIO pins factory defaults. So we don't need to go over how to configure the device using I2C from the laptop because we're just going to use the factory default settings. So I think I have enough information now to work on the schematic. So let's go back into KiCad. So thankfully, KiCad has a built-in symbol for this chip, so we're just going to use that. So we'll be powering the device ourselves, so it needs power and ground. There is some information in the datasheet on the internal power supply details. And if we look at typical power supply option using the 5V provided by the USB, you can see that we have to decouple VDD and VUSB and connect 5V to VDD. And then VUSB is going to be a 3.3V output. So I will not be using the I2C outputs on this chip. I just realized I should have inverted the transmit and receive because, of course, these need to be crossed. The transmit from the 2221 needs to go to the receive of the ACIA. There we go. Now for the reset pin, it says here in the datasheet that to take advantage of the power on reset circuit, we have to tie reset to VDD through a resistor from 1 to 10K. So for the USB configured pin, at the moment, I'm not going to connect it to the rest of the computer, and I'm just going to add an LED for it. There we go. And then finally, we need an USB connector. And I will be using a USB-A connector in this circuit. And actually on the breadboard, I'm going to use a pre-made adapter but for the PCB version, I will use a USB-A connector. So we can connect the D+ and D- lines directly together. We have to connect the ground, and because this is going to be a device, we shouldn't be connecting the shield of the connector. And then we're not going to be using the voltage provided by the USB ports, so VBus is also a no connect. Okay, so one small mistake. This should be a USB-B connector, not a USB-A. And then because I connected the IRQ output of the ACIA to the IRQ pin of the computer, I have to add a protective diode to the same output on the VIA, because this is a push-pull output, and so it can also drive the pin high. And this way, when the VIA drives this pin high, it cannot create a short to the ACIA. And on the breakout port, there is a 3.3K pull-up on the IRQ pin. And so this is going to make sure that by default, there is no IRQ. All right, let's go to the breadboard. Okay, so here is our computer where we left off the last time. Let's start hooking up the VIA. So the plan is I'm going to put it here on the top right, and then the space below is reserved for LEDs for the VIA, so I'm not going to use it, but I will put the oscillator for the UART over here on the side, and then I will add a breadboard on the top to connect the USB side. So let's first get started with hooking up the ACIA. So the ground is on pin 1, the power is on pin 15. So on pin 25 of the VIA is the clock, and that has to go to pin 27 of the ACIA. On pin 24 is VA, and that has to go to pin 2. On pin 23 is the IR select, so I'm going to take another jumper, and that's going to go to pin 3 here, and that's going to pin 14 of the 138 here. On pin 22 of the VIA is read-write, and that has to go to pin number 28. And on pin 21 is RQ, and so I have to change this. I have to add a diode. There we go, and then this can connect to the RQ line. I think it's a bit tight here, so let me actually move this. Now reset is on pin 34 of the VIA and on pin 4 in the ACIA. And then we need the 2 address lines and the 8 data bus lines. These are all the CPU side signals connected. Now let's connect the UART side signals. So DCD and DSR go to ground, that's pin 16 and 17, as well as pin 9, which is CTS. Then we need to connect the oscillator. It needs power and ground, and the decoupling capacitor. And then the output is on the top right, and that has to go to pin 6 of the UART. And then we have our receive and transmit, which is pin 10 and 12. And for that, we need the USB to UART adapter. Alright, so for the USB side, I will add a breadboard at the top here. I have here the MCP2221A, and I will put it here. Of course, we need to connect power to the breadboard. So this needs power on pin 1 and ground on pin 14. Then we need a decoupling capacitor to ground on pin 11. We need a 3.3K resistor to VCC on pin 4. Then pin 5 needs to go to pin 10 on the UART. Pin 6 needs to go to pin 12 on the UART. And then we have the status pins. And for that, I'll just use my LEDs with built-in resistors. I'll do green for transmit and receive. That's pin 2 and 3. I'll do yellow for USB config. That's pin 7. And red for I2C. And the colors don't mean anything. They're just so that we can distinguish them better. And then finally, we need the USB connector. And for that, I have cut up a USB cable and I've added a DuPont header in the end. And so for the USB cables, there is a color code. Red and black are power. And then the white is the plus and the green is the minus. So I have put some shrink tubing of the same color to the pins so that we know what they are. And I'll connect this here. So in black we have ground, that's the brown wire on the DuPont header. In white this is D+, and so that goes to pin 13, that's the red wire on the header. And then in green we have D-, and that's the orange wire on the DuPont header. And that goes to pin 12. Okay. So this should be all the wiring done. Let me plug the USB cable to my computer and see what happens. Yeah, of course, because the computer is not powered. So let me turn on the power to the computer. I'm seeing something on the configuration here. Nothing is happening. Also, I think I have the LEDs reversed. Okay, so yeah, so all the signals are active low by default, which is why the LEDs are all lit up now. So let me just reverse them. Okay, so we should see the orange LED light up when the device is configured. So we'll see it's trying something, but I'm not sure what happens here. Just going to do a quick check of the voltage. So it looks like the port is disabled. So I do have 5 volts here. So on the logs for my computer I'm getting failed to create device and then disabling port and then persistent enumeration failures. So I'm not sure what that means. Alright, so I had a hunch that maybe it was my janky cable here. That was the reason for not being able to configure the USB device. And so I went ahead and I got this little USB-B breakout board. So you have the V-bus, D-, D+, and ground broken out on a breadboard friendly header. And wouldn't you know it, but now it works. So if I turn on the power to the computer, you'll see that the device gets configured. Now, of course, because I'm connected to the TIN-C and to the MCP2221A, I have 2 USB modems here, and I have to find a way to differentiate them. And so I have this little script here that I found to be able to find which one of those is connected to the MCP USB-UART. And at the moment, it says that it's this one. So if I connect with Minicom to this, and I type on the keyboard, you'll see that the receive LED is lit up. So this seems to be working. Now what we have to do is update our assembly program so that the ACIA does something with the data that it receives from Minicom. And I'll do that now. So I've written a very basic initialization function for the ACIA. In here you can see all the constants that are used in the configuration. So I've reported all the binary values to configure various things on the ACIA from the datasheet. And this is so we don't use arbitrary constants. And we can always, have a descriptive constant instead. So there's a bunch of those. And then there's a very simple ACIA init function. First thing it does is programmatically reset the chip by writing the status register. Normally, this is only going to be called after a hardware reset, so this should do nothing, but I have it here just in case. Then we set up the ACIA control register with a number of settings. I picked the smallest baud rate that is supported by the MCP2221A, which is 300. We don't have an external receiver clock, and so the RXC pin outputs the baud rate. We have an 8-bit word length and 1 stop bit. And as you can see, I used descriptive constants here so we can always understand what this does. And then there is a second setting. We set the command register with the following. I'm not using the DTR pin, so we can set it high. I'm not using IRQs, so they can be disabled. I want to set up the device in echo mode, so I enable echo mode, and this requires that the transmitter is disabled, and so RTS is going to be high as well. And finally, we have to disable parity because this device does not support parity. So you can see that here. And that's the end of the init of the ACIA. So after that, it should echo whatever it receives back to the terminal. And I'm calling the initialization function over here when I initialize my other devices. So let's give it a test. Okay, so let's program the EEPROM. Now if I connect with Minicom, I'm connecting at a 300 baud rate to the MCP2221 device. And if I press keys, you can see that the LED are lighting up. And I have the echoed character on my terminal. So that's great. That signifies that the ACIA is working and it's currently echoing everything it receives back to the terminal. Okay, so we can also look at those signals in the oscilloscope. So I'm going to connect the yellow channel to the receive pin and the blue channel to the transmit pin. So we can set up the decoding function of the oscilloscope. You can see here I've set it up for UART. My signal is receive on channel 1, which is the yellow one, transmit on channel 3, which is the blue one. I've configured the baud rate to be 300 with 8-bit words, no parity and 1 stop bit. And the idle level is high and the bit order is least significant bit first. So now we can also set up the trigger to be on serial with the protocol of UART. We have the same signal assignments, and the trigger setting is going to be when we receive some data at the start of it, and same settings for the speed and format of the signal. And now I should be able to press a key in Minicom and have it appear on the oscilloscope. So if I press the letter A, you can see I have data coming here. Let me do a single capture. If I press the letter A, I guess I can zoom in a bit. So yeah, so we can see here we are receiving the letter A, which is 61 and ASCII hexadecimal. And immediately after receiving each bit, we are sending them back over the line to the computer. So that works. We can also overlay on this diagram the transmit and receive clock, because the SCIA is currently configured to output it on the receive clock pin, which is pin 5. So let me add that to the oscilloscope. So apologies, I misspoke. This is not going to be the transmit and receive clock, but it's going to be 16 times the transmit and receive clock. So it's going to be a 4.8 kilohertz signal, which is a bit less useful, I guess, in this visualization. Now let's go back to the assembly and try to write a more interesting program. Alright, so I've added some code to my SCIA driver. I have now two subroutines. One is called SCIA putchar, and this one will send a byte over the serial link, and it's going to do a blocking loop until the transmit is available before sending a character. And the second subroutine is SCIA getchar. This one receives a byte of a serial, and it's a blocking loop until something is received. So for putchar, it takes the byte to send as an argument in the A register. It starts by saving the byte to the X register, because we need to use the A register right after this. Then we want to wait until the transmitter data register is empty, and for that the SCIA has a bit that we can check whether it is set or not. If it's not set, then the register is not empty, and so the SCIA is still transmitting a previous byte that we sent, so we have to wait. And if it's set, we can continue, and we store the byte that we want to send in the data register and return the subroutine. And then in the background, the SCIA, we start transmitting this byte. For getchar, there are no arguments, but it will return the received byte in the A register. What it does is it checks the receiver data register full bit on the SCIA status register. And if it's not full, it means that we haven't received the byte, and so we wait. But if it's full, then we get the received byte by reading the SCIA data register directly and loading it into the A register and return. I'm making use of these routines here. Instead of printing hello world to the LCD, I'm now printing to the terminal. And then I have a loop here that will get a character from the terminal, and then it will print it to the LCD and send it back to the terminal. So we should see it appear on both the LCD and the terminal. And then it jumps back to getchar. So this is going to be an infinite loop. So I'm going to assemble this and test it. And spoiler alert, I know that it's not going to work, and we'll see why in just a minute. Okay, so let's program the EEPROM and see what happens. So the computer has reset, and it looks like in our terminal we don't have any hello world appearing. But if I type keys here, we can see that they are correctly echoed back to the terminal, and we can also see them here on the LCD. So what happened with the initial hello world string? Well, if we look at our oscilloscope, so I've set up a capture that will happen from the computer to the laptop. Let's see if I reset. There we go. So we can see in blue is the transmission, and it appears that it's trying to transmit the character 0. So something is clearly not working there. So let's see what happens if we remove everything but the first character. So let's program this and see what happens. Alright, so we're back at the beginning of our program, and if I reset, we can see that the H character is correctly transmitted. So what happens if I do two characters? Let's program this. Now I get the at character. And what happens on the oscilloscope then? So you can see here that it transmits the character 40, which is at. And with 3 characters, it's still an at. 4 characters, still an at. What's happening here is we're running into the known hardware bug of the W65C51N, the Western Design Center version. And the problem is in our putchar routine. You can see here that we repeatedly load the status register of the ACIA to know when we can transmit. So we want the transmitter data register empty bit to be set before we go forward with the transmission, because of course we don't want to overwrite what's already in the chip if it's currently being transmitted. Now the W65C51N has a bug where this transmitter data register empty bit is always set no matter what happens. And that means that this loop doesn't actually do anything. And so when we call putchar repeatedly without waiting for the transmission to finish, what happens is the next call will overwrite what's within the chip and it will corrupt the data. And so that's what we're seeing in our little test program here. So what we can do instead of this is after we transmit a byte, we can wait here for the byte to be transmitted. So with an 8 and 1 configuration, so that's no parity and 1 stop bit, we have 10 bits that need to go out per byte. That's the start bit, the actual byte data, and the stop bit. So at 300 baud, we transmit 300 bits per second, and so we have to wait 1/30th of a second per byte that we transmit. So our CPU is running at 4 MHz. So that means that we have to wait for 133K cycles to wait for that amount of time. So in order to do that, we can implement a simple rating loop, and we'll use the X and Y registers for this. And we'll have to load Y with a certain amount, X with a certain amount, and then decrement X. If X is not equals to 0, we go back to the decrement. If it is, then we decrement Y. And if it's not equal to 0, we go back to the beginning here. This is going to be 2 cycles. This is 2 cycles. Well, basically everything in this loop is 2 cycles. So let's say we load X with the maximum value. So the number of cycles that this loop will run at is 2 plus the value that we load into Y multiplied by 6 plus the number of times we loop for X multiplied by 4. So let's assume we set X to the maximum. Then Y is going to be equal to cycles minus 2 divided by 6 plus X times 4. And that's 1/30. So now this loop should wait 1/30th of a second, and it should let the ACIA finish the transmission before returning to the main program, and will be free to load another character. And of course, I need to move the RTS here to the end of the program. So let's try it out. And there we go. We have our Hello World now. And I can still type and see characters appearing on the screen and on the terminal. And so everything is working now. That's awesome. I'm pretty happy with this result. There are a few things that we can improve with the design. Specifically, it would be nice if the computer didn't have to waste time waiting for bytes to be transmitted from the UART, and if transmission was interrupt based. And so we'll see in one of the next videos what workaround can we implement to be able to use interrupts with the W65C51N, and that's going to free up all those cycles of waiting. And then the other thing I want to do is implement some improvements in our EEPROM programming. I still haven't implemented verification nor write protection, and I want to do some improvements to the interface with the laptop. So yeah, so that's going to be, I guess, the 2 next videos that come out. So stay tuned for those. In the meantime, if you have any questions or feedback about this video, please let me know in the comments, and I hope to see you in the next one. Goodbye.